This guy, Grothendieck, is somewhat of a mathematical idol to me, and I just love this quote, don't you? Too often in math, we dive into showing that a certain fact is true with a long series of formulas before stepping back and making sure that it feels reasonable, and preferably obvious, at least at an intuitive level. In this video, I want to talk about integrals, and the thing that I want to become almost obvious is that they are an inverse of derivatives. Here, we're just going to focus on one example, which is a kind of dual to the example of a moving car that I talked about in chapter 2 of the series, introducing derivatives. Then in the next video, we're going to see how this same idea generalizes, but to a couple other contexts. Imagine that you're sitting in a car, and you can't see out the window. All you see is the speedometer. At some point, the car starts moving, speeds up, and then slows back down to a stop, all over the course of 8 seconds. The question is there a nice way to figure out how far you've traveled during that time based only on your view of the speedometer? Or better yet, can you find a distance function, s of t, that tells you how far you've traveled after a given amount of time, t, somewhere between 0 and 8 seconds? Let's say that you take note of the velocity at every second, and you make a plot over time that looks something like this. And maybe you find that a nice function to model that velocity over time in meters per second is v of t equals t times 8 minus t. You might remember, in chapter 2 of this series, we were looking at the opposite situation, where you knew what a distance function was, s of t, and you wanted to figure out the velocity function from that. There, I showed how the derivative of a distance versus time function gives you a velocity versus time function. So in our current situation, where all we know is velocity, it should make sense that finding a distance versus time function is going to come down to asking what function has a derivative of t times 8 minus t. This is often described as finding the antiderivative of a function. And indeed, that's what we'll end up doing. And you could even pause right now and try that. But first, I want to spend the bulk of this video showing how this question is related to finding the area bounded by the velocity graph, because that helps to build an intuition for a whole class of problems, things called integral problems in math and science. To start off, notice that this question would be a lot easier if the car was just moving at a constant velocity, right? In that case, you could just multiply the velocity in meters per second times the amount of time that has passed in seconds, and that would give you the number of meters traveled. And notice, you can visualize that product, that distance, as an area. And if visualizing distance as area seems kind of weird, I'm right there with you. It's just that on this plot, where the horizontal direction has units of seconds, and the vertical direction has units of meters per second, units of area just very naturally correspond to meters. But what makes our situation hard is that velocity is not constant. It's incessantly changing at every single instant. It would even be a lot easier if it only ever changed at a handful of points. Maybe staying static for the first second, and then suddenly discontinuously jumping to a constant 7 meters per second for the next second, and so on, with discontinuous jumps to portions of constant velocity. That would make it uncomfortable for the driver. In fact, it's actually physically impossible, but it would make your calculations a lot more straightforward. You could just compute the distance traveled on each interval by multiplying the constant velocity on that interval by the change in time, and then just add all of those up. So what we're going to do is approximate the velocity function as if it was constant on a bunch of intervals. And then, as is common in calculus, we'll see how refining that approximation leads us to something more precise. Here, let's make this a little more concrete by throwing in some numbers. Chop up the time axis between 0 and 8 seconds into many small intervals, each with some little width dt, something like 0.25 seconds. Now consider one of those intervals, like the one between t equals 1 and 1.25. In reality, the car speeds up from 7 meters per second to about 8.4 meters per second during that time. And you could find those numbers just by plugging in t equals 1 and t equals 1.25 to the equation for velocity. What we want to do is approximate the car's motion as if its velocity was constant on that interval. Again, the reason for doing that is we just don't really know how to handle situations other than constant velocity ones. You could choose this constant to be anything between 7 and 8.4. It actually doesn't matter. All that matters is that our sequence of approximations, whatever they are, gets better and better as dt gets smaller and smaller. That treating this car's journey as a bunch of discontinuous jumps in speed between portions of constant velocity becomes a less wrong reflection of reality as we decrease the time between those jumps. So, for convenience, on an interval like this, let's just approximate the speed with whatever the true car's velocity is at the start of that interval, the height of the graph above the left side, which in this case is 7. So in this example interval, according to our approximation, the car moves 7 meters per second times 0.25 seconds. That's 1.75 meters, and it's nicely visualized as the area of this thin rectangle. In truth, that's a little under the real distance traveled, but not by much. And the same goes for every other interval. The approximated distance is v of t times dt. It's just that you'd be plugging in a different value for t at each one of these, giving a different height for each rectangle. I'm going to write out an expression for the sum of the areas of all those rectangles in kind of a funny way. Take this symbol here, which looks like a stretched S for sum, and then put a 0 at its bottom and an 8 at its top to indicate that we'll be ranging over time steps between 0 and 8 seconds. And as I said, the amount we're adding up at each time step is v of t times dt. Two things are implicit in this notation. First of all, that value dt plays two separate roles. Not only is it a factor in each quantity that we're adding up, it also indicates the spacing between each sampled time step. So when you make dt smaller and smaller, even though it decreases the area of each rectangle, it increases the total number of rectangles whose areas we're adding up, because if they're thinner, it takes more of them to fill that space. And second, the reason we don't use the usual sigma notation to indicate a sum is that this expression is technically not any particular sum for any particular choice of dt. It's meant to express whatever that sum approaches as dt approaches 0. And as you can see, what that approaches is the area bounded by this curve and the horizontal axis. Remember, smaller choices of dt indicate closer approximations for the original question. How far does the car actually go? So this limiting value for the sum, the area under this curve, gives us the precise answer to the question in full unapproximated precision. Now tell me that's not surprising. We had this pretty complicated idea of approximations that can involve adding up a huge number of very tiny things. And yet, the value that those approximations approach can be described so simply. It's just the area underneath this curve. This expression is called an integral of v of t, since it brings all of its values together. It integrates them.